This video, we're going to talk about energy. So this is still Unit 3, Work Energy Power. And we're going to talk about part number 2, or video number 2, we'll call it Energy Part 1, because we are going to have a couple of these different videos. So this first video is going to be a quick introduction to it, and maybe you won't be able to do the second learning target I have listed, but the learning targets we have are 3, I know what energy is, and 4, I can calculate the different types of energy. So energy is an interesting thing. So we'll call this point B and energy. So first one, A, was work, and now we're on B, which is energy. A couple statements about energy. We know like a definition for energy, maybe we've heard this before, but energy is the ability to do work. And yeah, that's a good explanation. But it's not always good to have words for your explanation. When we do physics, we like to have equations for our explanations too. So for now, though, we'll just say that energy is the ability to do work. Some interesting things about energy is that the term energy comes from a Greek word. Well, 2 Greek words, actually. It comes from the word, what is it? Energia. And this word I don't think it was actually used by the Greeks. I think it was used by someone in the medieval times. But then it became, kind of a portmanteau of 2 different words. So this word in Greek is Energia. Energia. And this has 2 different meanings to it, or 2 different words in it that make it up. The first word is en, or in Latin letters, it's en. In Greek, it would be e and then nu, the Greek letter n. So en means in. So in English, this is in, or doing. Or not I am inside the house, but I am engaged in something. The second part of this is a word called ergos, which is epsilon rho, gamma, omega, and S is, no, it's ergon, not ergos. And then, I keep screwing up my news. So it is ergon, not ergos, my mistake. So the ergon means work. And not like I am at my career type of work. It means I am at work doing something. I am in work. I am actively working. I am doing work. And so when we talk about energia, it means in work, but also this energy is the ability to do work. And that's what the name actually means, coming from the Greeks. So there's a couple of things that we could say about energy. First of all, energy is path independent. It doesn't matter what path I take to get from point A to point B. What matters is that I was at point A and I ended at point B. So when we talk about path independence, I'll draw a picture here. Here's a little table, and I have this mass on the table, and this mass is initially at some height y sub 0, and then I take the mass and I pick it up and I lift it some other distance to some final position y1. Now, when I do this, I increase its gravity potential energy, right? I'm changing the energy because it's further away from the Earth, and so it can fall, and it can develop more speed as it falls and all that stuff. So when I do this and I increase the energy, if I pick it straight up and put it there, that's one thing, right? It'll give me the energy, and that energy will just be that distance above the ground times some other stuff. But it doesn't matter if I picked it up and just lifted it vertically up, or if instead I started off walking with it this way, and then I did a couple loop-de-loops, then maybe another one, and then back over here, and then back to where I started, and then up over to here, and then finally end up at the same position. My energy will be the same between those 2 motions. That's what we mean by path independence. It doesn't matter the path I took to get there. What matters is where I started and where I ended. And so that is a really, really important concept in energy, is this path independence thing. If you have path independence, you have what we call a conservative system. And a conservative system is a system where energy is conserved. Energy conserved. Another thing about a conservative system is that only conservative forces act. So if I have a conservative system, then my energy is conserved and my energy initial is equal to my energy final. There are two types, or two broad categories I could put my energy into. The first of those broad categories I will call my potential energies. So potential energy. And the symbol that we use for any potential energy is the capital letter U. So U. And this right here is what I call my total potential energy. But there are other types. There are two types of potential energy. So maybe before we go on, we'll finish up this potential energy and we'll talk about some other types of energies. But let's say that I have a potential energy and I have a second type of potential energy that's from a different source. So maybe I could say that my total, or U, or maybe sometimes I'll write it as U sub T for total, that total potential energy is equal to the potential energy due to the first type plus the potential energy due to the second type. If there was a third type, I would just add that as well, a fourth type, all the way for all of my types of energy, where n is the nth. U sub n is the nth energy that's in my system. So potential energy, a lot of times in other classes, you might have heard it called PE or P or something like that, but we are not going to use those notations. We will use U. And the reason for that is because of this kind of notation. But if you go to a university, most of the time a professor will teach this with U instead of PE or P or whatever. A potential energy is just kind of an energy due to, we've called this like a stored energy before, maybe. So if you talk about how you can store energy in a battery, so there's some sort of potential energy there. You can store energy in a spring, there's potential energy there. You can store energy in a capacitor. You can store energy in an inductor. You can store energy in chemical bonds. There's energy hidden away in nuclei, right? We split the nucleus and we can produce nuclear power. But this is a stored energy, or a energy that can be converted from this form into a form that can do work. There are a couple types of potential energies, and we'll talk about them more in depth, but for now, we'll leave it at that. So potential energy, U, capital U, is our total potential energy, and then U with a subscript is going to be a specific type of potential energy. Moving on to the next page, let's say for number 5, there's another category of energy called kinetic. We will give this a specific symbol as well. It is capital T. Again, in other classes, maybe you've seen KE or K or something like that. Not going to use those, and the reason why is because the French who developed our SI, which is the International Systems of Standards and Measurements, the SI system that we use for all physics and really chemistry and all STEM heavy math, we use the SI system, and it was developed in France. And at the time, there's tons and tons of very brilliant mathematicians, guys like Poincaré, who really contributed heavily to the understanding of what energy is and how do we calculate it and how do we look at systems with energy. And so kinetic energy in French starts with T. And so we use T for kinetic energy. Then we use U, TU, for potential energy. Also, there's this idea of if I take a potential energy and I subtract it from another potential energy, so like the potential energy at point 1, and I subtract it from the potential energy at point 2, I will get this difference in potentials, and we call that V, and that comes from voltage, because a voltage is a difference in potential energy due to separation of charges. So we get T, U, and V coming out of it, and so it all lines up very nicely, but just to keep that notation, I will use T for kinetic energy, U for potential energy. There is no subscript for kinetic energy, it's just T. There's only one type of kinetic energy. Only one type of kinetic energy. And there are multiple types of potential energy, but there's only one type, well, for now. There's actually two, but that second one is a rotational kinetic energy, and it's very similar. And we'll talk about that next semester in the rotational motion stuff. So kinetic energy, we have potential energy, and we have energy that exists because of a conservative force. Conservative forces, when they act, they have that path independence as well. More importantly, if you want to know what forces are conservative, there's a bunch of things that we could talk about. They can be undone and redone multiple times. So they are reversible. These things are usually going to be internal to the system. If I define, if I define two protons to be my system, then that repulsive force between them would be a conservative force. The Coulombic force would be conservative. And the other thing about conservative forces is that we have an equation to describe them. No, there is a caveat to that. Friction has an equation too, but friction is a dissipative force. And these dissipative forces are just by nature always going to be non-conservative. So friction is non-conservative, and we have an equation to describe it, but again, it is not conservative. So our forces that we have equations for, you might think spring force, we had an equation for that. A gravity force, we had an equation for that. There's also this Newton's universal gravitation, F sub capital G. We have an equation for that. There's a couple others, like a Coulombic force, the strong nuclear force, and the weak nuclear force. These are all conservative forces. And we have equations that will describe them. But the other forces that are not conservative, for example, a normal force, we'll say these are all conservative forces, and we have equations for them. So the non-conservative forces, these are going to be like a normal force. We don't have an equation that describes normal force. We have to relate the normal force to a force of gravity, or force of gravity times some trig function, cosine or sine theta, and we have to relate them through Newton's second or third law, Newton's first or second laws have to be used to relate the normal force to the force of gravity, because we don't have an equation that just tells us this is the force of gravity or this is the normal force. Another type of force would be like a pull force, maybe a tension force, a push force, an applied force. All of these are words to describe some general force that we don't really know how to calculate, that we have to either measure it directly with some sort of device like a force probe or a Newton meter, or we have to relate it to another force that we can calculate. So we can pull at a constant velocity, and we can measure that pull force, or we could relate that pull force to friction. We can look at our normal force and we can say that it's equal to the force of gravity. We can say that maybe some push force is equal to some other force that we're exerting, or we can just measure them directly with an instrument. But all of these are non-conservative, and we do not have an equation for them. Non-conservative, no equations. And then again, the exception to that rule is friction, both static and kinetic friction. Frictions are always underlined and bold. Frictions are always non-conservative. Okay, so this is kind of what I wanted to get at. Maybe we should talk about some different types of energies. For instance, we've seen many of these energies, I'm sure, before. We'll talk about maybe thermal energy. And this would be like heat. So if you have heat, if you're hot, you have some thermal energy in you. Your body produces thermal energy. There's a certain amount of thermal energy in the air that we measure by calling it a temperature. And this thermal energy, this heat energy, cannot do work. It can never be used to do work. Well, that's not true, but in general, it cannot be used to do work. And when it is used to do work, it is such a small amount of it that's actually transferred into work that it's just practically nothing. So heat energy is pretty much the end of the energy ladder. It's the bottom rung or the top rung, however you want to think about it, but it is the last one, because once we reach heat energy, you're gone, game over, right? And as we started off, according to our recent models and ideas behind physics, and we say that there's some big bang and there's this massive explosion, and all the energy in the universe that exists today was released during that explosion. But eventually all of that energy is going to become heat energy. And when that happens, no energy can be left to do work, which means that you can't form chemical bonds, which means that you can't form DNA. You can't make cells. No life is possible at that point. Well, no life will be not possible long before that point. But once we reach that point, that is the absolute end, and time stops. There is no more time. It's a whole really interesting thing to think about. But thermal energy is the end, right? And sometimes we talk about this in terms of the heat death of the universe. But again, it is still energy. It still exists. In a sense, but it's not something that's really usable or recoverable. Some other energies that we might have, chemical energy. So we have chemical energy because of chemical bonds. A lot of times we approximate these as being springs, that attach to like two, if we have hydrogen, H2 gas molecule, the diatomic hydrogen gas, we could approximate those bonds as springs, and the energy that comes out of them is very similar to the energy that that you would see from a spring system. But these chemical bonds, when we break them, we release energy a lot of times, and that's what causes fire. That's what causes you to live because you ate something this morning. It's really, really super important for life. It's what makes your DNA a helical shape. It's what makes your body work, right? It's the energy that we store in ATP and ADP is because of that energy and that chemical bond. Another type of energy we could have is the nuclear energy. As you know, two like charges will repel. So if I have two protons, they will repel each other pretty strongly the closer I get them together. If I take a bunch of them and I squish them all into one tiny little bit in the nucleus of an atom, it's a ton of energy because they really don't want to be together. Something is holding them together, and that is nuclear energy. So this is the energy inside of a nucleus, or inside of a nuclei, the nuclei. So when we split uranium, all of that, to to maybe make a bomb or to produce energy or whatever we're doing with this radiation. All of that energy that radiates out is because it was stored into these, keeping these protons close together. And when we break that apart, there's a lot of energy there. And so it's released and all this heat comes out and all this light and sound and all kinds of neat things happen. Okay, so thermal energy, chemical energy, nuclear energy. There's some more types of energies we could get into. Let's see, what other types of energies can we talk about? There's several. Oh yeah, radiant energy. So radiant energy is like X-rays, photons, basically. So these are due to photons. Sometimes we could think of it as an X-ray, maybe a gamma ray. Not enough M's. Gamma ray. Visible light. Light that we see, as well as, UV light, infrared light, radio waves, TV waves, all those things are radiant energy. Furthermore, we could have other types of energy, but the ones that there was one more. That's right, electrical energy. So electrical energy is due to a charge separation. Whether it's two positive charges, two negative charges separated by some distance, or whether it's a positive and a negative charge that would be attractive separated by some distance, there's still separation of these two charges, and still there's a energy associated with that. Turns out that when we have like a wire, maybe I'll have a bunch of electrons in that wire and they'll be pushing on each other. So if one gets pushed hard enough, it will push on the next one, which pushes on the next one, which pushes on the next one. And we keep seeing that going down the line until it reaches our house and starts to do work for us by, powering our TV or our, kitchen appliances, dryers, washers, all that kind of stuff. So this is, in a sense, a separation of charge. Maybe you don't think about it that way, but if I kind of zoom in and I think about just one of those electrons, the electron would start at position A and it will go to position B when it moves. So it starts off here, and I'll just draw a dashed outline to show where it was, and it goes to part B. So when I'm at A, or when I'm looking at A, and the electrons move to B, now there's this hole there. And so the absence of this negative charge is the same thing as a positive charge. And then on B position, I have the electron itself, which has a negative charge. And so now in this wire, even though it's a bunch of electrons moving, I still have a separation of charge. Another way that we could see a separation of charge is something like battery terminals, where I have a positive terminal and I might have a negative terminal, and then there are some chemicals and an anode and a cathode in there, and then those different chemicals will cause a reaction and will cause a change, flow of electrons. But I'm still separating these two charges, and maybe if I put a multimeter here and here, I could measure a voltage, which is a separation of charge, which is due to a separation of charge, but a voltage is a difference in potential energy. So I'd have some sort of energy here, and I'd have some sort of energy here, and if I subtract them, I would get this voltage V. So it's this is what electrical energy is. Now, I want to talk a little bit about the radiant energy as well, because radiant energy is not energy. In fact, no energy exists in the universe. But we'll get to that in a moment, and it's really central to this idea of radiant energy as well. But there are three more types of energy I do want to talk about. So part number 12, we'll call that kinetic energy. Number 13, we'll call that gravity potential energy. So gravity potential energy. And number 14, we'll call that spring potential energy. And these three energies, I've done them in red for a reason. I wrote them in red for a reason. That's because these are the three things that we consider to be our mechanical energy. Total mechanical energy. And I'll get to that in a future video. Just want to point it out that these three things are important for us in this class. All the other ones are well outside of this class's scope and sequence. So when we talk about charge separation and that kind of energy, that's more of an AP2, APB type of class where they talk about E&M. The radiation stuff, that really requires more of a understanding of various near speed of light transforms and math that we have to do for that. But those, they're all kind of different, and they are something else entirely. But for us in this class, we will talk about these three energies as our mechanical energies, because they're energies that we can describe mathematically fairly easily, and they're also really, they do stuff that we've seen happen before. I don't know how to put it better than that, but they do stuff that we have seen happen before, and so we will talk about them for sure. Also, the math to analyze them is pretty simple. When it comes to energy, and this will be point number 15, energy does not exist. I know this kind of messes with a lot of people's minds, but energy is not a real thing. Nothing in the universe is energy. What I'm saying here is that forces are something that exists in the universe. You can interact with a force, you can feel a force, you can change a force, all kinds of things you can do with a force. It's a real thing. It exists in this universe. Charge is a real thing that exists in the universe. Spin, momentum, velocity, position, all of these things are measurable quantities, things that we can deal with. But energy is not. Energy only happens as a mathematical construct, so it is purely mathematical in nature. And there is no energy particle. There is no energy wave. It is just a mathematical concept. So why would we use energy if it doesn't really exist in the universe? Well, the reason why we do use it is because it's easy to calculate. It gives us useful information. And it's also very easy to measure. And these 2 points happen mostly because energy is a scalar. So there's no direction to it, right? We don't have to measure, oh, it's this much energy in this direction, or it's this much velocity and also this much mass. And then there's these directional stuff that happen, but it's losing mass, and right? But energy takes care of all of that stuff. It's very, very, very nice, very neat, and it works well. And so why we use it? Well, I mean, why do we use hammers? Because it works, right? There's rocks in the universe, just like there's, forces. And certainly there is sticks, just like there are distances. And there are ways that we can stick these things together, just like there's math. And we could stick a rock and a stick together, fashion them, hefting the stick and putting in between, and then fastening it down with rope or twine or something. And we can make a pretty good hammer for them doing that. But hammers don't exist in the universe, in nature, without humans creating them. And in a similar sense, energy is like a hammer, right? It doesn't exist in nature, but we have created it to use as a tool to talk about other things that are much harder to deal with, both conceptually and mathematically. So energy is a very, very useful topic. And we're going to get more into energy. We'll talk about these three red energies I have written here, the mechanical energies, so kinetic, gravity potential, and spring potential. And then if you remember back from that work video that I did some integration that you will never have to do, or you shouldn't have to do. I don't think it's on the AP exam at all. but we'll talk about the results of that integration and why it applies to gravity. So, or not gravity, but why it applies to gravity and spring potential energies. So stay tuned for that. Otherwise, I hope this was useful for you, and I'll get back to you with another video on energy part 2, where we'll talk more in depth about these 3 types of energies, and we'll do some calculations, maybe a practice problem video, and we'll talk about total mechanical energy in a separate video, and from there maybe a conservation of energy video. So again, hope this was useful, and we will see you later. Have a good one.